That second one, thanks. So tonight's lecture is Curiosity's First Year of Exploration on Mars by John Grotzinger, who's the Fletcher Jones Professor of Geology at the California Institute of Technology, Chief Scientist of NASA Mars Science Laboratory mission. Let me tell you a little bit about John, a little bit of history about him, and then I'll allow him to tell you a little bit about himself as well. But let me tell you from the perspective of how I know him. So it was a field trip about 25 years ago to the Guadalupe Mountains. If you've never been there, it's one of the most amazing places geologically in the entire world. And John and I met there. It was a field trip. We were assigned to be in the same hotel room. And we were about to go on this Permian Reef Geology trail, which takes you from this ancient Permian basin up to an ancient Permian reef in a one-day hike that's really intense and grueling, big change of elevation out in the desert. And I got a lot of sleep, and I woke up and I was looking forward to it. It was like 6 o'clock in the morning, and I look over, and John's not there. And I didn't know where he was. I thought he was out to breakfast or something. He came back in a little while. He just told me, oh, I just went out for a 5-mile run. This was before a really intense hike. So that told me he was really into it. He was really determined. Then John eventually became a member of the National Academy of Sciences. In brief, this is about the highest esteem a scientist can achieve in their career. It's usually people who have advanced the frontiers of science. That told me he's very creative, he's very intelligent. And the thing about the National Academy of Sciences is a lot of old guys with gray hair in it, because it's usually something after a whole career, a whole body of work. John was inducted at age 42, which is kind of like being, at age 11, the valedictorian of your high school class. And that told me something about John as well. But perhaps more than anything that I could do to introduce you to John is some prose from New Yorker magazine this year in April. Grotzinger has worked in Siberia, Namibia, Oman, Arctic Canada, among other locations. He's rafted rivers in Yakutsk, dodged grizzly bears and black flies around Great Slave Lake, and scouted rock formations on the Skeleton Coast, hiking more than 20 miles a day. The long months of solitude and open sky have given him a lean, wind-bitten look. And a laconic style rare among NASA's high-strung engineers, parentheses, Big Bang types, Big Bang Theory types. Watching him at work in the days leading up to the landing, I was reminded of Henry Fonda in one of his early westerns, squinting at the horizon and chewing over his options while the townsfolk galloped off in a dozen different directions. So that tells me he's someone who can keep it together under pressure. So please welcome John and Henry. Okay, we're going to keep that one on. Okay, got it going. Here's the webcast one. Got a pocket.
Great. Well, thanks, Jay, and thank you all for coming out tonight on Friday night. It's a pleasure to be here. I think I did this about 6-7 years ago for a different rover mission, and now we've moved on a bit, so I'll be telling you about the one that we're working on now. And to sort of start with, here's my title slide. And I know that you all come from different walks of life. I see some kids in here. We probably have some scientists and people that do other stuff. And, you know, I'm going to try to keep it general and touch on a number of different things that may have some value to you as an individual. So we're just going to take this all at a pretty high level as we go through the evening here. I wanted to start out by just pointing, we might have to dim the lights just a little bit more to see some of these graphics. That we're going to explore a place up here. This is Gale Crater. And if you look at all the craters that are around this area, only one of them has a mountain in the middle. And this is our crater. This is where Curiosity is. This crater is as wide as the big island of Hawaii. And it has a mountain in the middle, which is 15,000 feet high. So it's higher than any mountain in the lower 48. And we have no idea how it got there. But what we do know is that down at the base of that mountain, in the shadows here, is a rover 2 meters high, and her name is Curiosity. And it is my honor to tell you about her mission in the first year of exploration of Mars. what I wanted to do is start off and set the stage. How many people have seen the 7 Minutes of Terror? Okay, good. Most haven't. So you're in for a treat here. I'm going to let this video run. And all the people that you see in this video are real engineers from different walks of life. I'll talk a little bit about them towards the end of the presentation. And they are the people that really made this happen. They're the lead engineers for all the major subsystems of the landing system.
When people look at it, it looks crazy. That's a very natural thing. Sometimes when we look at it, it looks great. It is the result of reason, engineering, thought. But it still looks great. The top of the atmosphere, down to the surface, it takes us 7 minutes. It takes 14 minutes or so for the signal from the spacecraft to make it to Earth. That's how far Mars is away. So when we first get word that we touched the top of the atmosphere, the vehicle has been alive, but dead on the surface for at least 7 minutes.
Entry, descent, and landing, also known as EDL, is referred to as the 7 Minutes of Terror, because we've got literally 7 minutes to get from the top of the atmosphere to the surface of Mars, going from 13,000 miles an hour to 0, in perfect sequence, perfect choreography, perfect timing, and the computer has to do it all by itself, with no help. If any one thing doesn't work just right, it's game over.
Slamming into the atmosphere has developed so much aerodynamic drag. Our heat shield, it heats up and it glows like the surface of the sun. 1,600 degrees.
During entry, the vehicle is not only slowing down violently through the atmosphere, but also we are guiding like an airplane to be able to land in a very narrow constraint zone. This is one of the biggest challenges that we're facing, and one that we have never attempted on Mars.
Mars is actually really hard to slow down because it has just enough atmosphere that you have to deal with it. Otherwise, it will destroy your spacecraft. On the other hand, it doesn't have enough atmosphere to finish the job. We're still going about 1,000 miles an hour. So at that point, we use a parachute.
The parachute is the largest and strongest supersonic parachute that we've ever built to date. It has to be able to withstand 65,000 pounds of force, even though the parachute itself only weighs about 100 pounds.
When it opens up that fast, it's a neck snapping 9 inches.
At that point, you have to get that heat shield off. It's like a big lens cap blocking our view of the ground to the radar. The radar has to take just the right altitude and velocity measurements at just the right time, or the rest of the landing sequence won't work.
This big, huge parachute that we got, it will only slow us down to about 200 miles an hour. And that's not slow enough to land. So we have no choice, but we got to cut it off and then come down in rockets. Once we turn those rocket motors on, we're going to do something. We're just going to smack right back into the parachute. So the first thing we do is make this really radical maneuver. We fly off to the sun,
Diverting away from the parachute, killing our horizontal velocity and our vertical velocity, getting the rover moving straight up and down so we can look at the surface with this radar and see where we're going to land. And we head straight down to the bottom of the crater, right beside a 6-kilometer high mountain.
We can't get those rocket engines too close to the ground, because if we were to descend propulsively with our engines all the way to the ground and essentially create this massive dust cloud, that dust cloud could then go and land on the rover, it could damage mechanisms, it could damage instruments. So the way we solved that problem is by using the Sky Crater.
20 meters above the surface, we have to lower the rover below us on a tether that's 21 feet long, and then gently deposit on its wheels on the surface.
As the rover touches down and is now on the ground, that the sun stays, is there a collision force with the rover? We must cut the bridle immediately and fly to the sun stage to a safe distance from the rover.
So that video was released before we landed, and with some concern from NASA headquarters that we might be exposing the soft underbelly of the mission, which motivated us even more so to get it out. And in the 48 hours before we landed, there were over 50 million hits of this video. And after we landed successfully the next day, there was almost 1 billion hits that had crashed the server. And it turns out to possibly be the most watched landing of any mission other than the first one of Apollo. So a lot of people wondered. We were actually asked to come to the House Senate Commerce Committee and for Science and testify about what went right. So I wanted to throw in a little bit here because I know there may be some members of the audience who are involved in business, and this is a very important business. And the question is, what went right? So I wanted to sort of come up with a couple of bullet points. If you're a student, it is also important to distill out the lessons learned so that you can make sure you get it right the next time as well. The first thing is that you have to have a bold question. And so our question leads to a grand challenge, and it is the quest for extraterrestrial life. Our rover is not equipped to do that measurement directly. It follows something else that I'll talk about later. It's called habitability, which is to ask if you, in fact, had a microbe in this ancient environment on Mars, could it prosper and thrive? Future missions will now build on what we have done and eventually return rocks back to Earth. And with that, we will make steady progress towards this extraterrestrial life question. But the need to have complex instrumentation, including the quadrupole mass spectrometer that Jay was talking about, is why we wound up with Sky Crane. Because when you add extra instrumentation, the mass goes up. And when the mass goes above a certain number, a threshold, you have to land it a different way. And I'll talk about that in a minute. So that grand challenge that comes from science begets a grand challenge for engineering. The other one is that we have a zero tolerance for error, or as close to it as you can get. And we have this mantra that says, fly as you test, test as you fly. That's the equivalent of real estate being location, location, location. If you don't get that right, you're out of business. And so for us, we just keep on testing all the time. We do not use any operation in space that unless we validated it first on Earth. The third thing is that if you first fail, don't try again. You want to get it right. So what we do is we go back and we try to figure out if we failed because we built a device that just was manufactured incorrectly, it was assembled incorrectly, and the stresses were exceeded and it broke. Or if you make 100 more, well, 80 of them fail because the design is wrong. And that latter one is a very big deal because if you get to space and you find out that the design of a mechanism is incorrect, you don't have a chance to fix it. Whereas you can always go back and rebuild another unit and staple it onto the spacecraft and be good to go. We had that moment. And the important thing that comes out of that is to be willing to admit and expose your mistakes. In our case, we went back to NASA headquarters in 2009, and we had a failed design mechanism for all the motors, 39 of them on the rover, and we couldn't make it to the launch pad in time. And in this business of going to Mars, you get a launch window that lasts about 5 to 6 weeks every 2 years. And when you miss that, we had to delay 2 years. That's why we launched in 2011. And we recovered, we got the design right, and so far so good. Curiosity's doing fine with the new design. And then finally, a little lesson about science. Planning is everything, but plans are useless. People have heard that before. And by staying flexible, we believe it led to us with a rather rapid discovery in a place where we hadn't really expected to make a big discovery. And I'll be talking about that as we go along. Okay, life on Mars. So, this is the grand challenge. It's not exactly this. That's not what we're trying to do here. We have a simpler task, which is really trying to search for evidence of microbes. We believe that all the data that we've got right now points to pathways that could have led to the origin of microbial life on Mars. And if we ever got really, really lucky, we might be able to find evidence for it. Even if there's no life on Mars today, it is still an amazing discovery, potentially, that would probably change the way we think about humanity if we could ever demonstrate that life originated on another planet, even if it went extinct. So we're after the kinds of environments where microbes could have lived. That's what we're really trying to do with this mission. We're not looking for either fossil microbes or active microbes. We don't have the ability to do that with our science payload, but we can investigate and determine if there was ever an environment that would have supported life as we know it on Earth. Okay, heritage counts. What we're doing here, and the reason that we succeeded, is not because we started from scratch with no prior history. And what's really true here is that if we have seen farther, it is because we have stood on the shoulders of giants. All the missions before us, beginning all the way with Viking, were designed to explore the surface of Mars and look for specific things. Beginning then with the Renaissance period on Mars, which we are now in the golden age of, we have Sojourner rover, which was part of the Pathfinder lander that landed on the surface of Mars on 4th of July, 1997. And with that, we were back to the surface of Mars. But now, to build on Viking, we needed a mobile platform. So this mission was what was called a technology demonstration. All we had to do was test out two key capabilities. Could you build this six-wheel rocker bogie suspension that would flatten out the terrain in a way to keep the top of the rover level, because the energy source for it is solar panels. And it's not going to be any good if the sun's over here and the rover tilts the deck this way because you're driving over a rock. So the rocker bogie suspension takes out that differential topography. That mission was successful. It did a little bit of science as well, but mostly what it was doing was paving the way in the architecture of the Mars program for the next decade's mission, which was Spirit and Opportunity, which landed on Mars, two of them, in 2004, having been designed to last 90 days and drive 300 meters. Opportunity is still operating to this day, having lived 10 years and going 38 kilometers. So with that then, we see the heritage. Six-wheel rocker bogie suspension, solar panel for energy, but now it's got a mast because instead of the lander taking pictures of the little guy bopping around on the surface, this guy's going to go off on its own and say goodbye to the lander forever. And we looked at it disappear over the horizon and went on to the way of discovery there. And the goal of that mission was to look for evidence in rocks on the surface of Mars that would confirm something that we always thought from orbiters based on previous decades, which is that water once flowed across the surface of Mars, that it was an aqueous planet like Earth, but something happened and all that water went away. So now we're looking for evidence actually on the ground, in the rocks, to confirm that. And we did, and we got to go ahead to the next level. And so in the Mars program architecture, the next decade called for a mobile geochemistry laboratory that wouldn't allow us just to find water for the 1,000th time. It would actually allow us to study that water, that ancient water, its properties, and determine if this was the kind of environment that, in addition to water, also had the right ingredients to support life if it had ever originated on Mars. So that's what we did. You see the heritage six-wheel rocker bogie suspension. Now we can go over rocks about that high and not tip the rover deck. But the difference is this time we don't have solar. We have a nuclear-powered source. And it takes the heat that's generated by the plutonium-238 source, and there's a thermocouple that takes that heat and converts it into electricity. We generate about 100 watts of power from that. And from that 100 watts, a light bulb in your living room, we get all the power we need to drive the rover. Okay. So here's our baby in the test bed, and getting back to test as you fly and fly as you test, one example of what we're doing, this is a full integrated systems test. The first time we did it, we put everything together on the rover, and in a system, what that means is the individual parts, you can test them individually, but you don't know how the thing as a whole is going to behave until you put them all together. So what we've got it in this chamber at JPL, it's called a thermal vac chamber. It creates a vacuum at times and we can test things there. But what we're doing here is a thermal test. where we illuminate the rover with a light source that has the same intensity that the sun does on Mars. And this engineer, who's in a white suit because you don't want to create a thermal anomaly, has a wand, and they take this wand and they reach out and they touch the various parts of the rover to see if the measured temperature agrees with what the predicted temperature was. Because you've got basically the length of this rover is about 10 feet. And it's made out of aluminum and titanium, which is a lot of metal. And the daily temperature variation on Mars is 100 degrees centigrade. During the day, the high barely gets above freezing, and at night it plunges down to about minus 90. And with all that metal, things are expanding and contracting, and we want to drill holes in rocks with a drill bit the size of your finger. And while we're drilling, if we need to keep going the next day, we don't want the rover yanking back on the drill. So we have to understand the thermal behavior of the rover, and this is a great example of that. The reason for the sky crane is because we're landing a car on Mars. Just to give you a sense for this. This rover literally weighs a ton. And so with that, we had to innovate and go beyond the designs that we had for previous missions. And so I just wanted to talk a little bit about that to give you a sense of what the challenges were. Now, you might have gleaned from the video, I call this slide powers of 10. So what we do is we enter the atmosphere at about 10,000 miles an hour, and the friction on the heat shield dissipates the momentum on the vehicle until the velocity is about 1,000 miles an hour. And then Anita Sen-Gupta was teaching you that she and her team made the largest supersonic parachute to ever fly to space in order to slow this massive vehicle that weighs a ton down to about 100 miles an hour, where the heat shield then falls off. The rover pops out on a rocket backpack that then flies around until it's going about somewhere between 1 and 10 miles an hour. So imagine that you're moving as fast as you can walk on a sidewalk, and that's how fast the rover is hitting the ground, tethered out on the end by the sky crane. So all of that requires, to slow it down, you needed to come down on rockets. That was the point that Tom Rivellini made, is that the problem with the Martian atmosphere is that the gravity of Mars is big enough to pull you down a lot harder than the moon did to the Apollo astronauts, but the density of the atmosphere isn't great enough to slow the vehicle down, so you need this extra mechanism. Otherwise, you're going to hit the ground going 100 miles an hour if you just land on a parachute. That obviously isn't what happens on Earth, so we have to deal with that difference in atmosphere there. And this leads to this expression that my friend Adam Stelzner, who is the lead engineer for the Entry, Descent, and Landing System, I think the greatest lesson learned of all, of taking risks. Some of you students here, at some point in your career, you may have to take a risk. And you will be challenged as you do that. And we went to headquarters and we got knocked back. When the team first presented this design, everybody thought it's crazy. That's why the video starts that way. Because that's what we were told. Those guys studied it. They determined in the end that it was actually the way to subsume a lot of risk and minimize that. And here's the reason for it. These are different landing mechanisms that we tried in the past. So here's one where we go all the way back to Viking. You land on legs. And what you see there is the heritage of Apollo. The Apollo astronauts learned how to land on legs. And you've got a human pilot that's basically directing the LEM as it lands, and it's interacting with the terrain, and the human pilot is pretty good at feeling what the ground is feeling as the thrusters impinge on the ground. And so one way to land is on legs. But for the rougher terrains that we want to get into, the problem is when the rocket engines are pushing down on the ground, if the terrain is uneven, one end is pushing up, the other end is sinking down. It's a really complex guidance and control problem. And so it turns out that for Pathfinder, these guys, the light bulb went off one day and they said, you know what, this is technology that's left over from the era when you wanted to get off the surface again. And if you want to go better, faster, and cheaper, let's just bury the things in airbags and crash land it. That was amazing, you know, and everybody goes, yeah, why not? So, you know, that was relatively easy to get away with, except the problem is now for Curiosity weighing a ton, at the impact that it would feel, there is no material known to man that would withstand that force and actually prevent the airbags from exploding. So they had to reject that and move on. So they went back, they talked about legs for a while, and then they talked about something called a pallet, which turns out to be an evolutionary dead end, because the rockets are underneath the pallet. And like Anita was saying in the video, the problem is those rocket motors, when they get that close to the ground, they're drilling to China. the exhaust on these rockets is like Mach 8 as they come out, and there's material moving over, and you could be slinging golf ball-sized rocks against the side of the rover, which is no good. And that's where the idea, I like to call it Rover on a rope, comes from. You dangle the thing down, and you got enough propulsion to keep you suspended and let the thing down, but the impact force is not great enough to send things ricocheting against the side of the rover. That was the idea behind that. The other thing about it is, instead of a couple of legs that are all trying to distribute the balance, you know, what's happening is all the awkward motion that may be happening as this thing touches down is basically sent back into a single cable. And so the descent stage is reacting by just accelerating up and down to smooth it out. So in the end, it's actually a very elegant way to do it if you can get beyond the fact that it just looks crazy. Okay, so here's what it gets you. And this is all the landing ellipses going all the way back to Viking that what you would see superimposed on top of our Gale Crater landing site. And this place was a landing site for Spirit and Opportunity as well. And you see that as we develop our ability to control and guide these systems, that we get better and better at reducing the landing ellipse, till finally, with Opportunity, it's small enough that we can sink it in this valley between the topography, the mountain range that the crater rim makes, and the mountain in the center that we're interested to explore. So it nestles right down in this valley that you saw in the first picture that I showed. So that's a graphical way to show how far we've come in being able to control these spacecraft. Whoops. Yeah, here's the next video. I actually want to stop for a minute. I meant to introduce this a little bit by saying you're now going to see excerpted from the 7 Minutes of Terror the parts of the animation that tell you what the spacecraft is doing that we can't possibly observe. And it interlaces it with what was really happening on the night that we were landing. And you will see pictures occasionally that are taken by a descent camera, which is under the belly of the rover. So as we're coming down, you're going to see real pictures that were taken at exactly the time that they occurred as we were watching these events on Earth.
Good. All right, Andrew. Vehicle reports entry interface. At this time, the pressurized propulsion system to increase the thrust in the system. We use that for relative maneuvering in the atmosphere. We're about to. We're standing by for guided start guided entry. We're navigating to feel the atmosphere as we go in here. The vehicle just reported via phone that it has started guided entry. At this time, the vehicle will see its way into the target. We have seen peak deceleration. Starting its first sector. It's reporting that we are seeing G's on the order of 11 to 12 Earth feet. We are not getting telemetry from altitude. We should have pressure deploy around Mach 1.7. Pressure is deployed. We are decelerating. The initial section has separated, but we're not on the ground again. We're down to 90 meters per second at an altitude of 6.5 kilometers per second. Standing by for fractional separation. We are in higher flight. We're at an altitude of 1 kilometer per second. Standing by for stacking. Stacking starts.
You remain strong.
Left shaft in front. Proceed.
Today, right now, the wheels of curiosity have begun to blaze the trail for human footprints on Mars. This is an amazing achievement.
Well, today on Mars, history was made on Earth. The successful landing of Curiosity marks what is really an unprecedented technological tour de force. It will stand as an American point of pride far into the future.
So what was amazing about this is that we got high scores even from the Romanian and Russian judges. Okay, so here were those thumbnails. So the second sort of eruption of joy that you saw was, you know, a bunch of noises and tones and people in blue shirts getting excited. And by the way, we all went back to our day jobs at Best Buy. Is when the pictures come down. And, you know, the one on the left was the first one to arrive. It's my favorite because we got this 10 seconds after we landed. And it was programmed that the camera would go off and take a picture. And we had programmed an orbiter to fly overhead at the right time, grab that picture, and ricochet it back to Earth. And through the dust, we knew that there would be a lot of dust flying around, and that was true. And we have some shields on there, some lens covers. And even through that, you get a sense, is this our mountain that we came to explore? And then 39 minutes later, we command the rover to take another picture, intercept with another orbiter, and send it back to Earth. You can see the length of the shadow increase on the rover. The sun is near setting at this time. And here is Mount Sharp. This is where our mission of exploration was supposed to begin, maybe about an 8-mile drive away as the crow flies. We were supposed to head on over there and see what it looked like. And so we went to work. The EDL engineers, as people that you saw in the video, they were immediately unemployed in the best possible way. They went off and had an all-night party, and the science team went to work because the sun goes down on Mars, and we get to work on deciding what we want to do on our first day on Mars. And that's the way it works. And so we work out a phase with the Earth for about 90 days, and we live in rooms. You know, the odd thing about Mars is that it rotates once every 24 hours and 39 minutes. So if you follow sunset and sunrise on Mars as the time of day, the time in the universe when you want to do science on Mars, every day you get in the airplane and you fly 2/3 of a time zone to the west, and you get jet lagged every day. And you go in and out of phase with the Earth. And so after a while, you come back in phase. You see your kids and your spouse, and then you slip away again, and you go off to a hotel, paint the windows black, and sleep during the day. And the reason why is because it gives us the most time to plan what we want to do. So we went off and we did that night. And then we all did go to bed. And when we got up the next day, the day on Earth had come and gone, and we were waking up late in the afternoon, and we got on the internet and saw that the world was watching. And these statistics began to roll out about how many people were paying attention to what we had done. And we realized immediately that this was one definition of success of the mission. No matter what we found scientifically, how could you lose with stuff like this going on? Because, you know, these are the people. You are the people that are paying for all of this. And if you're having fun with it, then we all win. Okay, so here's our field area. This is Mount Sharp. You can see our landing ellipse down here at the bottom. It's 20 kilometers in length. It's about 12 miles. And in the middle of it is the dot where we landed. It's ever so slightly off. So basically, that error in navigation from Earth to Mars, 351 million miles, you tee off in Tokyo, and you're aiming for the tower at UT, and you land in the Geology building. That's about the magnitude of that error. So these guys are pretty good at this stuff. All right, and so our goal was then to drive out of this ellipse, get through this black field of sand dunes, and then crawl our way up and investigate the rocks that were down here near the base of the mountain. That was our primary mission goal. So the data started to come down. We commanded the rover to take pictures, and the first thing we saw was the rim of the crater, which in our interest in the mountain we had almost forgotten about, and it turned out that it is spectacular. Of all the places we ever landed on Mars, this is far and away the most interesting. You look out, this is old Mars in the foreground, lumps of black rock laying around on a gravelly plain, and then in the distance you see these mountains going up, you see valleys coming down. It turned out these were carved by water. And then out in front of it you see layered rock, you see strata out in front there. And it looks a little hazy. In fact, it reminded us of, if you've ever driven from Las Vegas to Los Angeles, it looks like the Basin and Range province. Little LA smog coming in here to make it feel like home. We actually felt very comfortable looking at these pictures. And then the next day, we got the other half of the 360-degree panorama down, and this is what we saw. And I agree. I think this has to be my favorite picture. No matter what we find after this, in terms of the impact that it has on you, you just realize that this place, at some level, is just not that much different from Earth. And it's our job to figure out how it's similar and also how it's different. But what you see here are buttes and mesas. And instead of gravelly Mars with rocks strewn around, or even the Basin and Range, we've now got the Four Corners. You could be up in northern Arizona at some point. It almost looks like a set out of a John Ford film. And these buttes and mesas are eventually where we're going to be exploring, probably starting about a year from now. In about 6 months, we're probably going to wind up down here somewhere. And we're going to work our way up through here. You see these layers? It's like looking down into the Grand Canyon. And so for us, it's kind of like imagining what it would have been like for John Wesley Powell to be the first Westerner to go down into the Grand Canyon, look up at these rocks as a geologist and say, what does this all mean? And we don't really know what it means, but what from orbit, what it tells us is that all the layers that you see down in this part of the mountain have water in their mineral structure. They're either sulfates or they're clay minerals. And then when you get up to this level here, the planet seems to have dried out. Maybe it became the state that it's in today. All these rocks up here don't have any water associated with them. And if we can get up to this boundary, maybe, just maybe, we'll figure out why Mars lost its atmosphere and became dry and went off in an evolutionary course that was totally different from what happened to Earth. And that is the biggest question I think we can ask of all of this issue of habitability, and if life evolved on Mars, how it might have evolved, how it would have gone from there. Okay. Back to the rover. So the time came, what we do is start checking stuff out. And this went on for about 3 weeks. We turn on a system, check it out. Do the next one. You do them one at a time because you don't want things to interfere with each other. So the time came eventually where we were done taking pictures and we had the chance to use our laser. So we've got a laser on this rover that reaches out up to about 10 feet. And it basically burns a hole in the rock. And in that light that is created as it's burning the hole, we look at that light and it tells us in sort of a qualitative way about what the composition of the rock is. This is a powerful instrument because then it tells us whether or not there's something interesting there for us to go up and take a look in more detail. So we looked around. The sky crane did a good job of preventing us from landing in any place that would immediately look geologically interesting. So we get flat, gravelly Mars. And here's a rock about the size of the hockey puck. That was the biggest thing out there that was close enough to take a shot at. So we went for it. Took a shot at the rock. And now we have done this almost 100,000 times. And pretty much every time you see something like this. We command the robot to shoot the laser at the rock. And then afterwards we take pictures to see the shot points of what we actually analyzed. And this is the typical hole that you get. It's about 1 millimeter in diameter, about 1 millimeter deep. The dust gets blown away, you get down below the surface, and then you get the rock. And this is an array of 4 spots. So here's the second one down here, looks the same. Here is the third one down here in the corner, it looks the same. But the fourth one, something interesting happened at this shot. A little explosion occurred. So you get what looks like a crater, it is a crater, and it reflects the fact maybe there was something in that rock. Maybe there was a fluid inclusion that had water in it. The laser tunnels through, and suddenly all that volatile explodes. So we think something like that happened. A little pinhead-sized inclusion maybe got triggered to explode. I can promise you that's the most exciting thing that we've ever done with this laser. But again, the world is watching. And people are having a great time. I can tell you can find even more interesting stuff than this. Just put in laser, curiosity, cat, you'll find all kinds of interesting stuff. That's my kid's favorite. So, again, people are having fun with this, and no matter what we find, they're going to invent their own universe, and that's perfectly good. Okay, so this is the issue about what then happened to the mission as I get into some science here. We have this canyon that we look from orbit, and it looks just like every other canyon that we think once flowed water on Mars. But out in front of that canyon is a feature that geologists call alluvial fans, and probably most people are familiar with this. It represents a washout. As the water pours out of the valley, it takes sediment that it's eroded up here in the mountains and spreads it out down here on the plain. The flow spreads out and all the dirt dumps out. And so we can see that feature, and where the landing ellipse was, we can plot something else. It's a property called thermal inertia, and the easiest way for me to explain it is imagine it's a cold fall day and you're downtown and you walk past a building and it's about 6 o'clock in the evening. And you walk past a building and you feel that heat coming off the building. That's what this is a map of. And whatever's going on in this whole area here, these rocks down in here that are colored red, they're glowing late into the night. And we don't really know what that means. We're not sure we still understand what it means, even though we've been there now. But for us, it's a beacon. The fact that you've got this stuff out in front of this stuff suggests that maybe it has something to do with water. And if we land close enough to it, let's check it out. So we landed right where the cross is, and it turned out it was only a couple of football fields away to go check it out. So we drove in exactly the opposite direction that we were supposed to go to. And this was a big team discussion. With 473 people, scientists, on the team, everybody has their opinion about what to do. Everybody gets their chance to be involved in the discussion, and we talk about it long enough until we can reach consensus about what to do. And so we turn around to the sponsor, NASA, who represents you guys as taxpayers, and we're going to now drive off in the opposite direction and drill a different oil well. That's basically what we propose to do here. And I'll tell you about what happened. Okay, so here's where we landed. You look down now. This is another one of these orbiter images that was taken by a camera called HiRISE that has 3 color channels in it, false color. So this is not real color. This is false color. And there's Curiosity. And remember, she's painted white. So from orbit, we get a very bright reflection off the deck of the rover. And then you can see on the left, on the upside and the downside, if I get the laser away, you can see where the rockets blew holes in the soil anyway, even though we were 7 meters above the surface hovering there. And then all this stuff represents where the dust got cleared away on the ground because the rocket plumes were pushing all that stuff away. So we drove away and across here to go to this point where we saw, and you don't have to be a geologist to get this, here's one terrain, and it's kind of rolling hills, and it's sort of hummocky. We call it the hummocky terrain. And then you've got another one down here that looks like the surface of the moon with all these craters preserved in it. We call it the crater terrain. And then we've got another one up here with all these light tone fractured features in it. And we call it the light tone fractured terrain. And the important thing is all 3 of them come together. And it's just 5 football fields away. So you add all that up, and it was just irresistible. And we felt that this stuff in particular, this is what's glowing from orbit. And it's like telling you, come to me. Let's check this out here. So we went down into a feature, a topographic depression here that we called Yellowknife Bay. And as we descended down into there, we made observations. But first, as we were driving along right here in the hummocky terrain, one day we looked down, and here is a rock out in front of the rover. And you look at this rock, and it looks like a piece of concrete. Just go downtown, look at an urban construction project. People get a jackhammer up, lift up the sidewalk. You look in the side, what do you see? A bunch of rounded pebbles that are all cemented together. And so in our case, that's exactly what this was. And what it's the result of is an ancient river flowing along. It turned out that the rover landed right on the money unit where there's an ancient river that was leading downhill into what we were hoping might become an ancient lake, which would be a really good place to look for a habitable environment. So now the scent is hot, and we're following it along and continuing to literally go with the flow and drive downhill. Here's a rock on Earth. This rock is only about 10 million years old, which is really young for the Earth. A bunch of rounded pebbles in here, all cemented together. And here's this rock from Mars, which is 350 million miles away and almost 4 billion years old. I can tell you that is the oldest conglomerate you will ever see on any planet. I'm certain of that. And here's how it forms. We could imagine a very conservative scenario where Mars is generally dry all the time, like it is down in the Atacama Desert in Chile. And here are the Andes Mountains, and every once in a while there is enough moisture that it does rain there. And when it rains, you get a flash flood. The water flows out of the mountains, down into the valley, through an alluvial fan, and the blocks of rock that were weathered out up here in the mountains get transported along. They bounce against each other, knock the corners off, and get rounded. And so that's what we're looking in that last picture, is basically an ancient river that was flowing along, transporting bits of rock the size of golf balls. Okay, so then we got to the point where we drove across far enough to look out into this basin that we were calling Yellowknife Bay, where the rocks were glowing from orbit. And when you cross this border right here, the world changed for us. Instead of going from sort of loose rocks, gravel, and sand, suddenly we go down to bedrock, and now we get a totally different terrain on Mars that looks like Moab, Utah. You almost want to get your mountain bike out here, go cruising around these bedrock hills. It turns out when you go down into this stuff, that's where you hit the jackpot. And so we've just got some papers that came out a few weeks ago that represent a first installment. And we've got some that are in review now that will discuss what we found down there. But on the way down, we actually had to test out all of our instruments to make sure we were ready to drill. And so before we were ready to drill, we wanted to scoop up some sand and work with that because it's an easy material. And here's the results. They were all published in Science 2 weeks ago. We even made the cover of the Rolling Stone here. And what you can look down here is where the arm reached out. This is a self-portrait, by the way, the same way that you would make one yourself. You stick the camera out in front, we reach our arm out, aim it back at ourselves, smile, take all the pictures, and after 54 pictures, we then move the camera over to here, take 3 more pictures, and then use those in Photoshop to wipe out the arm. So you can't actually see your arm in the picture. So that's how we made this, no arm, and it looks like somebody walked up and took a picture of Curiosity. But you've got these 4 scoops down here, and you can see that scoop 1 we did on Sol 61. So Sol is a Martian day, 24 hours, 39 minutes. And that occurred on Earth on October 7th. And over the course of a month, we processed and scooped 5 samples. And you can see the first 4 right here. The first 2 we rejected. So we take it, we put it in the sample processing system, which has a bunch of sieves in it. Imagine a flour sieve that you would squeeze to have the flour come out of it. It's a very similar thing for us. And what we want to do is use the dirt on Mars to clean both sides of that sieve. So we take the sample processing system and we move it around in these Tai Chi-like motions on the rover and move it around until it's coated and covered everything, and then we dump it out. So here we've scooped it, here we've dumped it. Here we've scooped it again, second time, dumped it out. Then the remaining 3 samples and the 5th one, which is not in this picture, go into the rover and go into the instruments. And in that, we not only practice how to use our laboratory, but we're actually studying these surface materials on Mars. And I'm not going to say anything more about that. You can go to Science and read about everything we found in there. It was pretty interesting. But in the interest of time, I'm going to move along. So we then drove down into the Yellowknife Bay area, down to these rocks that were down at the bottom of the basin, and we found a place to drill. So the geologists, we have a list of hundreds of names that we picked for, in this case, it was for northern Canada. And on any given day, whoever's on duty, picks the name, selects one, and that becomes a target that we shoot at with a laser, or we put the arm out and make a measurement. And so these were some of the names that we picked out that were potential drilling sites. And then the engineering team got to work and figured out what they wanted to, where the best place was, and they called it drill. Now, that's really the way to do it. So off we went, and we drilled this hole, and here's what we got. This is the first drill hole on another planet, done by a robot. The last time this was done on any planet was on the moon by Apollo astronauts who held a handheld drill and did it that way. So here we go down. We told the rover to drill, potentially for up to an hour. And the drill basically works like the kind that you buy at Home Depot, where you take it that extra step and lock it, and then it percusses a little bit. So as the drill bit's rotating around, it's also getting hit on the back side, and it works its way down into the rock. But rather than an hour, This thing cut through this thing like a knife through hot butter. In 7 minutes, we had drilled, our total depth here is 6.7 centimeters, but it took 7 minutes to get there. This thing was a really soft rock, and right away we knew something was going on here when we got the engineering data back that told us that this rock looked soft. The next thing that happened was we got the picture of this that showed us that not only the hole, but all the cuttings from the drilling were gray. And that was a big thing for us as a mission, and here's why. Also, there's veins cutting through here, and you can see this array of points. That's where we backed off with the rover and shot it with the laser. So we acquired all this data, hoping to hit one of these veins, and we did it right with this analysis right up here, and it turned out that vein was made out of calcium sulfate. So the scent was getting even warmer here. You put this all together, and I can distill the science down as simply as possible. Here's what we've got. When I was last here in this room talking about what Opportunity found, I would have been showing you this picture probably around 2006, 2007 then. But it would have been a story about how we ground a hole, not with a drill, but a grinder. Think about taking a piece of sandpaper and just rubbing it in place for about an hour. That's what we do. So you shave off maybe a fingernail thickness worth of rock there, shave it down, and what you see there is that the rock is red, and the dust that you made is also red, and that's because the rock has hematite in it. So every beginning geology student knows that if you go and you take a piece of porcelain, and you take a rock that has hematite in it, you scratch it on the porcelain, it turns red. So when this thing ground the rock away, we were doing a hematite scratch test, and basically, this is red Mars. And instead, what we found with Curiosity is what I like to call gray Mars, and this is what a decade of science gets you. You're able to predict now from orbit a little bit better about where to go to drill your wells. And so from that, then, we sink the well, and we go from red Mars on the surface. Mars is red because of the dust. The dust is red because it's got iron in it, and it's red to our eyes because the iron is all oxidized. That's important. Remember that as we go along here. We knew from using the laser that there was iron in the hole, and when we put the other instruments down to measure the powder more quantitatively, they confirmed that there was iron in there, but now this iron is gray. So if you are looking for habitable environments on Earth, the places that you want to go to, especially the ones that might have organic compounds preserved, if there was anything left over, either abiotic or biotic in the rock, you don't go to red rocks, you go to gray rocks. And so this is from an ancient lake basin, about 250 million years old, outside Princeton, New Jersey. And these rocks are the ancient river deposits, and these gray rocks are the lake deposits. And so basically what we did here was we worked our way from the ancient river down into the ancient lake, and we drilled into the lake bed and found out that there's an environment that looks surprisingly Earth-like. This one turns out to be not very Earth-like, except in extraordinary circumstances. Okay, so I want to get you into a little bit of science data. So what we're going to do here is bake a cake. I'm going to walk you through this graph. So we've got the sample temperature. We take the powder, we stick it into an oven, and we heat it up. And as we heat it up, the volatiles come off. And then the volatiles we feed into the instrument that Jay mentioned, quadrupole mass spectrometer, and we look at the signal. You don't have to know what this instrument is. Basically what's happening is we heat this thing up, the volatiles are coming off. So the first thing that's coming off is carbon dioxide, and the next thing that's coming off is oxygen, but the very first thing to come off is water. Think of a cake. You come into the room, you come home, somebody in the house is baking a cake. You walk in the room, before you even see anything, you can smell it. The reason you smell it is because the sugar that you put in the cake mix is beginning to caramelize. And then you go in the room and it feels a little humid in there. That's because the water came off. And then the cake hasn't flopped, it's risen because of the baking powder you put in there. Guess what's in the baking powder? CO2. And when you heat it up, all that CO2 is basically coming off and making bubbles that cause the cake to rise. So this is basically the same thing that's happening. We heat the sample up, these volatiles are coming off, here's the carbon dioxide coming off, here's the oxygen coming off, here's the water coming off, but most importantly, the water does not drop down as we continue to heat it up. As we get to really high temperatures, the water kicks in again. There's a second peak there. And that second peak is associated with clay minerals that we were able to prove were there with a separate instrument called X-ray diffraction that I won't get into. But that shows us what the minerals that were in there. But the other thing that was really interesting is that we see two forms of sulfur here. And the one form of sulfur is oxidized. So it's sulfur in the most oxidized state. The other one is called sulfide, and it's sulfur in the more reduced state. And so what we have for the first time in the history of exploration of Mars is we see iron in 2 different oxidation states, and we see sulfur in 2 different oxidation states. Here's why that's important. Back in 2006, when I was here, I would have finished this talk by showing you what Opportunity had discovered in the way of an aqueous environment. Yes, the rover found an ancient environment where water once flowed. But if you were there on Mars, this is almost certainly what that water would have looked like. This comes from a place in Spain called Rio Tinto, where since before the Roman times, there was sulfide minerals that are being oxidized, and they turn to sulfuric acid, and the pH gets so low that it gets down to about pH 1. And in an almost unimaginable way, a certain kind of microbe can actually live there. So yes, this place can actually be habitable, but just narrowly so, and by one particular microbe. This water is red because all the iron in it is actually fully oxidized. Because the pH is so low there, it's actually dissolved. It's kind of amazing. It's called Rio Tinto, and the river is red because this iron is in the fully oxidized state. What I'm going to show you this time that Curiosity found is a very different view of Mars. And you're going to have to get rid of this grass because we don't think there's any grass growing on Mars. But we've got a more ordinary Earth-like analog now. Here is a place along the coast of Western Australia where there's a lot of rock called basalt. And when that rock weathers, it forms basins that fill up as lakes. It's not always wet. So I kind of like this because we don't know that Mars was always wet, but it doesn't have to be always wet to be a habitable environment. And if you dig down and you get a shovel full of this stuff, mineralogically it has exactly what we found at this place on Mars. A lot of the primary igneous minerals have weathered away, and now they are instead replaced by clay minerals. And in there, this is black because the sulfur is reduced in there. And so this kind of material, if it becomes a rock, will make a gray rock someday. So the most interesting thing is that not only was this an aqueous environment, but it was also one that had a neutral pH, and it was also one that was very fresh water. So I'll explain that with honey and batteries. The issue about the place that we discovered back in 2004 is that not only was the pH low, it was extremely saline. And it was so saline that we don't actually think that anything could have lived there. And it wasn't saline because of table salt. It was saline because of another kind of salt called magnesium sulfate. And here's an example of a discovery of water on Earth. Honey has water in it. But the thing about the water in this honey is that the activity of that water is so low that nothing can grow in it, including microbes. So the reason you don't need to put honey in the refrigerator is because the water activity is so low that the microbes, if they dropped in there, they'd have all the water sucked out of them. So this is not a habitable environment, even though it's wet. But what we found down in Yellowknife Bay was something where the salinity was also very low. So the water activity was actually quite high there. It seems like Earth. The clay minerals tell us that it was a neutral pH. And the last thing is, the easiest way to explain this for the kids that are out there is imagine a battery. It's got solid material inside here, and everybody knows that if you put a wire at this end and a wire at this end and put a light bulb in the middle, the light bulb will glow. Well, it turns out that there's certain kinds of microbes on Earth. They're called Chemo Lithotrophs. They actually live by chemicals in rocks. That's what the litho means. Chemicals from rocks cause these organisms to live. So basically, those chemicals are things like minerals that have iron that is both reduced and oxidized, and minerals that have sulfur that is both reduced and oxidized. And so our rocks are like chemical batteries on Mars that if there had ever been a microorganism there, it could have lived if it was one of these chemolithotrophs. So we actually believe for the first time on Mars we've been able to use a rover to demonstrate that this could have been habitable in just the same way that these microorganisms live on Earth. Here's where we're going, and I wanted to give you a shot again of my favorite picture from where we landed. And if Curiosity was over there and we kind of used the telephoto lens to zoom in a little bit more, there's a boulder that's rolled down the cliff, and it's this one right here. So if you can see that dark dot there, that's about the size of the rover, and you can see that we've got a very long drive ahead of us to go up through these hills and work our way up to where that boundary occurs. That's where we're headed. And as I finish up here, I wanted to leave you with a couple of thoughts. This is one of my favorite quotes from Teddy Roosevelt. Far and away, the best prize that life has to offer is the chance to work hard at work worth doing. I think that's what we do when we do exploration. And it doesn't have to be on Mars, although for this trip on Mars, you guys get to come along as the taxpayers on this journey with us and explore Mars. We have 17 cameras on this mission. Every one of the pictures that we take is sent out to the public within 24 hours of it landing on Earth. 3 months after we make a measurement, we send all the data out for the public to look at independently, to get into scientifically, or just to enjoy spending time working on. And this is important. Exploration is important because I think it's where we as individuals stretch ourselves, we extend ourselves, push us out of our comfort zones, and we do it because of our curiosity. So that's really an important message to leave behind, to just follow your curiosity as you do these things. And I have to acknowledge my colleagues here, because this is a team. We often hear about teamwork, and it almost gets to be so trite it doesn't have impact. But I want to leave you with this group of 200 scientists that I get to work with every day that I go to JPL. I don't go into Caltech very often. And this is an extraordinary group of people because of their backgrounds. They're all really smart, but they all have different backgrounds. They all have different things that they were interested in when they were younger. They all liked science and engineering. They liked these space missions because that's how they got stimulated. And so basically they all come to work every day to work on this rover. And I wanted to single a few out just because you saw them in the video and you may have read about them. You know, here's Mohawk guy. So Babak Ferdowsi is a second-generation Iranian American who happened to go to MIT and learn guidance and control. Anita Semgupta is second-generation Indian who basically is the lead engineer for designing the Supersonic Parachute. And Adam Stelzner, of course, Elvis guy. You know, Adam had a punk band and didn't even go to college. And then after about 10 years, he actually went to community college, and then from there, one thing led to another. And Jody Davis is the mathematician who's in the back room sharpening her pencil and doing all those calculations for that tee-off from Tokyo. And then, of course, you know, we've got Greg Collins over here. He started out life as a geologist. He was an amateur paleontologist who just got interested in rocks and fossils, went to college, got a geology degree, and after that decided to do something a little bit different. So these are all normal people who work on these things. And so for those of you that are in the audience, if someday you want to do this, you can do it. And my last point is something that really I thought is perfect for the times that we live in right now. Time magazine covered our landing, and they asked at the time, what can we learn from a robot that's 154 million miles away? And what we do is we learn about ourselves. That's this mission of exploration. And this is a powerful message to get across, and I think the quote that I took from that article is perfect with where we wind up at this particular week in history. In an era in which the grind and gridlock of Washington have made citizens wary of anything the government touches, the spectacular success of the Curiosity rover is a reminder of what the country can still do. So thank you for listening. Yeah, right there.
With recent budget cuts to NASA and hopes for the government funding more space exploration slim, do you believe that there's a future for space exploration like private space exploration?
Yeah, the question is there a future for private space exploration as government funding levels drop? I do think there is a role for it. You know, they're playing the game right now of near-Earth orbit and launching commercial space satellites. But I can imagine an era in which some of these guys are very interested in philanthropy. They would like to invest in something that might be a science mission. And there are many things that you can do that are scaled down from this that involve robots that are, kind of in the better, faster, cheaper mode, where for a couple $100 million you could actually do something. So I tend to think that there's a future there. Just a matter of time. Yeah, right there.
General overview, can you talk about the process of choosing where to, how do you decide to go to people, do you choose a place or the time frame that you sit in a room and try to decide?
Yeah, so the question is, how do we decide where to drive the rover on any given day with 473 people all weighing in? It is a big challenge. That's what I mostly do for my job. And it's one that's very democratic. It starts out with an over-guiding strategic vision. You can't have a strategic vision by deciding tactically what you want to do each day and then hope that those dots all add up to a path that leads you somewhere important. So you have the overarching goals that you set for the mission. So for us right now, it is to pack it up in Yellowknife Bay, drive as fast as we can to base of Mount Sharp, and then from there work our way through the rocks. And so it begins with that, and we have a lot of discussion about as many people that are in this room right here, and we converge on a plan, and we converge on a time scale that we would like to execute that plan on. And then from there, we have what are called strategic planners that break that down into month-by-month and week-by-week bits. And then we have the tactical process where we execute day by day what it is that will add up to the week-by-week and the month-by-month plan. So it's very nested in terms of that process, and it takes a lot of effort, but people buy into it and it works well. Yeah, right behind you there.
In order to accomplish what was done, someone had to be able to dream. And if you were to dream about the success of this mission, what would that dream look like? That if you were to be able to find X, that it would really have surpassed your expectations?
Yeah. The question is, if I could dream about what I would personally like to see happen on the mission, what would that be? And I think that there would be two things. We are in the search for extraterrestrial life, and we have to approach that in a rational, step-by-step way, and you have to make sure that those steps are deliberate and well-focused. So what we have had cut out for us as part of the mission definition is to search for habitable environments. Our what's called level 1 requirements state that this mission should find one habitable environment. Well, we did that 8 months into the mission by driving in the opposite direction. So now what we've decided to do in a team, and we just made this decision a few weeks ago at an all-hands team meeting where everybody flew in, is to go to the next level, which is now to try to find habitable environments that might also preserve organic carbon. And that's important, not because we might find something that represents a molecule of life if it had evolved on Mars. We don't have any way to determine that. But it tells us that we found the right chemical environment that if life had existed, you could have preserved it as a fossil. And that's important because if we go back to Earth and we go back to rocks that are billions of years old, on a planet that we know has been teeming with life for at least 3.5 billion years, you don't just pick up a rock and find evidence of it. You don't even find complex organic molecules. So there's a recipe book about what you have to do to find the right materials that leads you into that. And I think that if we could find an organic compound, I think that would be our finest moment from here on out, right here in the front.
Of course, there have been a number of probes that have gone to Mars, but I'm sure there's some debate about maybe should the next probes go to maybe one of the moons of Jupiter or Saturn. How does that debate get resolved?
Right. So the question is, how does NASA go about deciding whether to send a mission to Mars or the outer solar system? I can tell you that that is an active debate, and the organized approach to it is what's called the decadal survey, which happens once every 10 years, and all the planetary scientists in the community get together and they debate and they propose missions, and those missions get costed. And so Mars always tends to win the lion's share because it's close enough that you can do it less expensively and you can repeat every couple of years. And so right now, in terms of that competition, the mission that has won out is called Mars Sample Return. Well, it's actually called 2020, but the idea is to launch in 2020 a series of missions that would result in returning a rock to Earth, because that will force the technology to get something off the surface of Mars, which is a precursor to human spaceflight to Mars. Yeah, maybe one over there, right over there. Purple shirt, there you are. How far up the mountain is the rover planning to go? We are now working on a proposal that will get sent into NASA that will propose for the next 2 years. When we get there, we're going to work our way up through about 250 to 300, 400 meters, something like that, and travel a distance of about 4 to 5 kilometers across the ground. And then after that, we might eventually, in the next extended mission, be able to work our way up to where the evidence for water in the rocks goes away. Maybe one right there. Say that again? The question is, after what amount of testing will it be time to put man on Mars? And the answer to that is there's two things that go along. One is the development of the technology to get a spacecraft off of Mars. And although there's a lot of talk about one-way trips these days, as far as we go, we'd like to get people back. And I think that the other thing that goes along with it is understanding what the environmental conditions are that you'd be wrestling with. Because if you go to Mars, it's an 8-month one-way trip to get there. Then you have to wait almost a year and a half till you can actually make it back to Earth. So you have to spend a lot of time on the ground. That means the astronauts would have to find a source of water to be able to produce. And that's one of the things about finding water in rocks all the time is actually a good thing for that. So we carry an instrument called the Radiation Detector, which is measuring the amount of radiation an astronaut would experience if they were walking around on the surface of Mars. So from that, we can calculate the dose rate that an astronaut would experience to help guide the development of spacesuits for the surface of Mars. Yeah, right there. Are there any tektite like rocks on Mars? So a tektite is a feature that forms when there's an impact and rocks melt and the droplets go spraying everywhere. And we do drive around in the soil. In one of the science papers that just got published, there are little glassy balls for which the leading idea is they could be something like a tektite that would reflect glass falling around on the surface of Mars. Yeah. How about right over there? I don't know, you tell me. I saw a cartoon one time that said, so I've heard scientists have found evidence for life on Mars, and the next frame shows, who would be interested in that? And the third one says, geologists. You know, I think it's one of those questions that's open-ended, but it's a little bit similar to what happens in astronomy when you find out Earth isn't at the center of the solar system. You know, it makes you think about your own place in the universe.
Hey, John, here's a question from a teacher watching Region 13 in the Texas Regional Collaboratives. Are there any future rovers that may be sent to other planets? That's from Beth.
Any plans for future rovers? So right now they're all headed to Mars, but I have a favorite mission concept that if I wasn't caught up with Mars I would be advocating, and it's sailboats on Titan. So Titan is a moon of Saturn, and it has solids, liquids, and gases that are all made out of hydrocarbons. So they have ethane and butane lakes on the surface of Titan, and the wind blows. There's sand dunes on Titan. So the idea is you could build a cheap rover. You know, maybe this is where we get one of these SpaceX guys to bankroll a mission to Titan. All you got to do is land a boat on Mars and let the wind blow it around from shoreline to shoreline, and you can discover stuff pretty cheaply.
All right, we have a final question for John before he has to head off to the airport.
How about right there?
Why does it take so long to travel? Like one of the pictures you were saying, it would take like 6 months or a year to get to the next location. Why does it actually take that long to travel?
Right. Because of the speed of light issue, you know, it takes anywhere between 9 and 20 minutes to get a signal one way from Earth to Mars, depending on how close the planets are. So we don't ever joystick the rover, so it has to drive by itself. And there are two ways that we drive. One is what's called blind drive, when we as humans can look at the pictures and as a team of people, it's not one person, assert with great authority that there is nothing in the way, and then you tell the rover to drive that 6 feet before you get nervous about it, and then tell the rover to go into auto nav, where it drives about 2 feet, takes the pictures with stereo cameras that are like our human vision, and then from that it builds a digital terrain model of the topography, and then it asks the question, is it too rough to drive on? Then if the answer is it's okay, then we drive another 2 meters, take the pictures, build the digital terrain model, and then we compare the two data sets. And so it's always differencing the two data sets to see if we get above a threshold for what's considered to be too risky to drive, and then it stops. And so that time that it takes for the robot to think and do this autonomous navigation means we really can't get much more than a football field and a half on any given day, on a good day.
Great. Well, that